Hey, welcome. This is the first lecture in linear algebra, and the main material in the first lecture is to introduce the determinant. And the concept of determinant is derived from solving the linear equations. For example, we consider a11x1 plus a12x2 equals to b1, together with a12 is a21x1 plus a22x2 equals b2. Uh, for x1, x2, and a11, a12, a21, a22, b1, b2 all being real numbers, but x1 and x2 are unknowns. The algorithm in dealing with such a problem is the elimination. For example, if we choose to eliminate x2, then we multiply a22 to the first equation. So let us call the first and the second. And we multiply the a12 to the second equation. So that is 1 times a22 equals a11 a22 x1 plus a12 a22 x2 equals b1 a22. And the second equation times a12 equals to a21 a12 x1 plus a12 a22 x2 equals to b2 a12. So so this is 3 and this is 4. If we use 3 minus 4, we will have a11 a22 minus a21 a12 times x1 equals to b1 a22 minus b2 a12. And similarly, we can eliminate x1. So this is for x2, sorry. And for eliminating x1 is the same. So we multiply the first row by a21, and that is a11 a21 x1 plus a12 a21 x2 equals to b1 a21. And the second row, the second equation times a11 equals to a11 a21 x1 plus a11 a22 x2 equals to b2 a11. And if we use 5 minus x use, so x1 cancels out, and that becomes a12 a21 minus a11 a22, and times x2 equals b1 a21 minus b2 a11. So if we let C, so this is for x1, if we let C defined by a11 a22 minus a12 a21, that is this guy. So if this guy does not vanish, then we have a solution for x1. So x1 therefore equals to b1 a22 minus b2 a11. Sorry, b2 a12 over a11. So that is C, right? Since we have a representation. Okay, so now let us calculate for the solution of x2. So so that's C1. So C2 is defined to be A12, A21 minus A11, A22. So if this guy does not vanish, we will have x2 equals to C2, and C2 is divided by, it is B1 A21 minus B2 A11 over C2. So obviously C1 does not equal to 0 means C2 does not equal to 0. So such a number in determining whether our linear system has a solution or it is consistent. In saying a linear system is consistent would mean that the linear system has a solution or multiple solutions. In saying it is inconsistent would mean it has no solutions. So we can derive the concept of determinant. So the determinant, we can say C defined by A11, A22 minus A12, A21 in the above is the determinant, and we shall use the notation A11, A12, A21, and A22 to represent this difference. So let us do an example. So the first example, if we are going to calculate lambda 1, 1, 2, lambda, and we want to find out the lambda such that the equation, the determinant does not vanish. So by the definition, we know lambda minus 1 times lambda minus 2, this guy does not vanish, which means lambda squared minus lambda minus 2 does not vanish. And this could be represented by lambda minus 2 times lambda plus 1. And this guy does not equal to 0 means lambda either not equal to 2 or lambda not equal to minus 1. And since the term determinant is derived directly from solving linear equations, we can use this determinant to solve the linear system. So, an example. Suppose we are going to solve the linear system 2x plus 5y equals to 1 and 3x plus 7y equals to 2. So we may write it as a determinant form using only the coefficients of the linear system. So that is 2, 5, 3, 7. And this guy, by definition, is 14 minus 3 times 5, 15. Is minus 1 does not equal to 0, which means we have a solution or multiple solutions. So therefore, we may apply these two equations to solve the to find the solution. So first of all, since we are going to calculate B1 A22 minus B2 A12, we may write it still in the form B1 A12 and B2 A22. And this guy, obviously, so B1 is 1, B2 is 2, and A12 is 5, and A22 is 7. And this guy is equal to 7 minus 10, which is minus 3. Similarly, we can calculate the other side, which is yield by 2, 1, 2, 3. So this guy is 4 minus 3, which is 1. So therefore, since our C equals to this guy, so the first solution is minus 1, minus 3 over minus 1. That is x since we are calculating x and y. So that is 3. And for y, it is 1 over minus 1, which is minus 1. So we can see that in calculating the solution of the linear system, we simply replace the right-hand side by the first column, that is the coefficients of the first variable, and then we can find the corresponding denominator of the solution for x for the first variable. Similarly, if we replace the second variable, the coefficients of the second variable by the right-hand side, we can yield another solution, another denominator of the solution. So our algorithm in solving the linear equations is first we find the determinant of the linear system to find out whether it's vanishes or not. Since if it vanishes, then we have no solutions. So if the determinant is non-zero, we can proceed by these two equations to find the solution of the linear system. So we just worked out for two variables. So now we generalize it to more variables. Let us do three variables. So let us consider a11 x1 plus a12 x2 plus a13 x3 equals to b1, and it's a21 x1 plus a22 x2 plus it's a23 x3 equals b2, and a31 x1 plus a32 x2 plus a33 x3 equals b3. So we still apply the algorithm in solving the linear system with two variables. And we just see that our determinant, if we denote by D, is A11, A12, A13, A21, A22, A23, A31, A32, and A33. So instead of a direct calculation in two variables, we now have a different form. So how do we solve this more complex determinant? The algorithm is quite the same in what we are doing with the two variables. We do the elimination tricks, and the calculation is quite complex, but it's not. It's very trivial. So we, for example, cancel x1 and then x2. Then we have a solution for x3. So after applying this similar result in deriving the formula for 2 by 2 determinant, we have the formula for the 3 by 3 determinant. A13, A21, A32 minus A13, A22, A31 minus A11, A23, A32, and minus A11, A22, A33. So that is we use this guy plus this guy, and then plus this guy, and minus on the other side. So perhaps I should, so anyway, uh, and then let me use brown, and minus this guy, and then minus, perhaps this guy. So, and then lastly, we minus this guy. Okay, so let us do an exercise, perhaps 3. Yes, 3. So we now determine the value of lambda such that the determinant lambda 1, 0, 1, lambda 1, and 0, 0, 1 does now vanish. So we apply the algorithm for calculating such a 3 by 3 determinant. So we see that lambda squared, so lambda squared, and times 1 times 0 times 0 plus 1 times 1 times 0. And we know that they're all 0. So on the other side, we have this guy being 0, this guy being 1, so we have a minus 1. And the other side is also a 0, since it's lambda times 1 times 0. So we have lambda squared minus 1, which is lambda plus 1 times lambda minus 1, so which means lambda equals to plus or minus 1. And similarly, we can use this to solve a 3 by 3 linear system. So, for example, we have x1 plus x2 minus 2x3 equals to minus 3, and 5x1 minus 2x2 plus 7x3 equals 22. 2x1 minus 5x2 plus 4x3 equals to 4. So we still write it as a determinant form. We have 1, 1 minus 2, 5 minus 2, 7, 2 minus 5, and 4. So this guy is just 1 times minus 2 times 4 plus 1 times 7 times 2 plus minus 2 times 5 times minus 5, and the minus 2 minus 2, 2 minus 5 times 1 times 4 minus 1 times 7 times minus 5. So this guy is minus 8, and this is 14, and this is 50. So we have 64 and it's 56. And for here is minus 8, and this is minus 20. And for this guy is plus 35. So we have 15 minus 8, which is 7. So this guy equals to 63, which is non-zero. So we have solutions, and we can proceed to find the solutions. Since we have 3 different variables or independent variables, we may denote it for the x1, d1 equals to, we replace the first, the column consisting of the coefficients of x1 by the right-hand side, which is minus 3, 22, and 4, with all the others remain unchanged. So this guy is just 63. Anyway, I may have, yes, it's 63. So we have x1 equals to 1, since it's the minus D1, and similarly for D2 and D3. So we can use the the solution for the linear system. And we will leave this as an exercise since it consists only very simple calculations. So now we are able to solve the linear system with 2 or 3 variables. Let us now generalize it to n variables. So we first need to introduce the determinant, the formal definition of determinant when n is greater or equal than 2. That is, we have more than 2 unknowns. So the definition of determinant. So for n greater equals to 2, the determinant of an n by n matrix. Yes, so in this form, it's the determinant form is not matrix form. And we shall later use this bracket to represent the matrix form. But still, to most people who are already exposed to the terminologies, the representation of matrices, we shall say this with bracket is an n by n matrix, even though we have now no formal definition for matrix for now, but don't worry, we will cover that later. So let us just use the terminology matrix just for notion. So for a matrix A, with its entry being Aij, with I represents the row and J represents the column. So the determinant is the sum of n terms of the form being plus or minus a, say 1 j, and determinant of a 1j, with plus and minus signs alternating, where the entries a11, a12, and a1n are from the first row of A. So in symbols, so let us just use the strict symbols. So that is the determinant, we use determinant of A, or this looks like the absolute value of A, but since A is a matrix, we use this notion to represent the determinant of that matrix or that linear system. So all these two guys are defined by Lj ranging from 1 to n of minus 1 to the n plus j times a1j times the determinant of a1j. Okay, so let us do an example. So if we are to calculate the determinant of a 1, 5, 0, 2, 4, minus 1, and 0, minus 2, 0. So let us interpret this definition since it is not very familiar to people who are exposed to this terminology for the first time. So let us say that our determinant A equals to, for example, if we are choosing the first row, that is 1, 5, and 0. So that means we use the first row. That's, for example, A11. So if it is A11, then it is 1 plus 1, which is 2, so it is a plus sign, and times A11, which is 1, and times determinant of A1j. And in finding the determinant of A1j, for example, A11, So this is A11, and we start with this guy and remove this row and remove the corresponding column. So the remaining 4 terms becomes our determinant of A1J. So that is 4 minus 1 and 2, 0. And obviously, this guy equals to, okay, let's solve this later. So, and the other one, so we have now defined, and so this is for the symbol. So 5 is in 1, 2, right? So it's 1 plus 2. And times the 5 and times, so this time we start with 5 and we cancel the row and corresponding column and use the determinant generated by 2 minus 1 and 0, 0. Now for the last term, it is 0. So that is A13 is 0. So we do not need to bother writing this down since it vanishes out the anyway. Okay, so now let us calculate this guy. So this is a 2 by 2 determinant. This is to calculate this guy. So this one is 1, and this one is 1. This is 4 minus 2, minus 2, which is 2. So it's 2 plus, and this is minus 1 times 5 times a 0. So did I do everything right? Oh, yes, I did something wrong. So this guy is minus 2, since it is this guy. So this is minus 2. So the solution is minus 2. So therefore, in practical terms, we would like to use the row uh, and respectively use column with as many 0 as possible. And now we shall introduce the matrix, which is called the triangular matrix. So for example, A, B, 0, 0, C, D, sorry, that's 0. Sorry, A, B, C, 0, 0, D, E, F, 0. And all the way down to all these guys containing for this data. So that is the matrix with a form for this containing non-zero elements and all these containing 0 elements. So this is the lower left triangular. So we have the form looks like this, the form looks like this, and the form looks like this. Also the form looks like, looks like this. And in calculating the determinant of the triangular matrix, we have a formula which turns out to be very useful. That is minus 1 to the n times n minus 1 over 2 times a1, a2, all the way down to an. Suppose we're doing an n by n matrix where a1, a2, and an are just the values on the diagonal, only on the diagonal. And similarly, for the array with non-zero elements appearing only on the diagonal, we have, for example, a1, an, with all the others being 0. So it is just a1 times all the way down to an. And now we shall talk about the properties of the determinant. And before that, we need one key terminology called the transpose of the matrix. So the transpose, for example, A is defined by A11, A12, A21, A22. The transpose of A equals to, by moving the column to the row, that is A11, A21, and by moving the second row to the second column to the second row, so that is A12 and A22. So let us calculate its determinant. It is A11, A22 minus A12, A21. And we have A transpose equals to A11, A22 minus A12, A21. So one direct observation is that the determinant of A equals to the determinant of its transpose for a square matrix n by n. And also, if we apply the transpose to the transpose itself, we get A itself. So now we arrive at the first result in the first lecture. This is called the row operations. So first of all, if AI is one row of A, where A is an n by n matrix, which is added to another row to produce B, then the determinant of A equals to determinant of B. And the second is that if two rows of A are interchanged to produce B, then we have the determinant of A equals to minus determinant of B. And the third result is that if one row of A is multiplied by K to produce, where K is a constant, to produce B, then we have the determinant of A equals to, K times the determinant of A equals to determinant of B. And also, we have another theorem. So the first theorem allows us to do, since in calculating the determinant, we wish, whether starting with a row or starting with a column, that we are dealing with as many zeros as possible. So theorem 1 gives us a very technical and powerful result so that we can eliminate to get as many zeros as we want, so that we can simplify the calculation of determinant. And the next result is the operation of matrix. It's the change of the determinant on the while we are doing operations of matrix. So, for example, if A and B are both n by n matrices, then first of all, we have the determinant of A equals to determinant of A transpose. We have seen that in the two variables case, and this holds in general. And also, we have determinant of A, B equals to determinant of A times determinant of B. And know that we have a stronger result in multiplication of matrices, which the multiplication of two matrices is the determinant equals to the multiplication of the determinants, respectively. However, for addition, since in algebra, addition has, in a way or not, before perform better than multiplication. That is, most properties holds in addition does not hold, or some results hold are valid in addition do not necessarily hold in multiplication. But this is quite counterintuitive that the determinant of A plus B is not necessarily to be equal to determinant of A plus determinant of B. So to compute the determinant of the sum of matrices, we shall need other techniques, but it does not simplify in the same way as the determinant of a product of matrices. So now introduce some results, more results. So A is n by n matrix, and there are two rows respectively for columns that are equal to each other. Then we have the determinant of A, 1-ish. And the second is that if there are two rows, respectively, columns are such that one is a multiple of the other, then we have the determinant of A, 1-ish. And thirdly, if there is a row, respectively, for columns with all the elements being 0, then we have the determinant of A equals to 0. So this theorem offers us the criterion in determining whether the determinant of an n by n matrix 1-ish. And even though we do not have a law for the addition determinants, we still have some methods in turning this into a addition-like formula. So this is another theorem which allows us to do some trick in calculating the determinant. So still we're supposing A is n by n, then the determinant of A equals to suppose. So let us say, suppose A is such that, since we're saying it's a matrix, it's A11, A12, and all the way down to A1n with, so suppose there is a row called I, so we have ki1 plus ai1 and ki2 plus ai2 and all the way down to kin plus ain and all the way down to an1, an2 to ann. Then the determinant of A equals to the determinant of, so let me just use the determinant form. So it equals a11, a12, a1n, and ki1, ki2, kin, an1, an2, ann, plus a11, a12, a1n, and ai1, ai2, ain, an1, an2, ann. So that is, if we have a row with this row behaves like it behaves like an addition, then the determinant of the whole could be divided by this form as long as it satisfies this condition. So we have another theorem. So this is theorem 4, and we have theorem 5. So if A is still n by n, and if we want to multiply one row, respectively, column by k, and add it to another row, respectively, columns, then the determinant remains unchanged. So that is, we can, for example, in elimination, we multiply one row by the same constant and add it to another row. Of course, our determinant remains unchanged, otherwise we cannot use this algorithm in solving the linear system. So in fact, the determinant function, if we regard it as a function, it has a linear property. So for example, still, n by n matrix A, and we consider determinant of A as a function of n columns entries, for example, n column entries in A, and we will show that if all columns except one are held fixed, then the determinant of A is a linear function of that one entry variable. So suppose the jth column of A is changing, it's not fixed, with all the others being fixed. And we can write A as A1. So A1 represents the first row, and A j minus 1, x aj plus 1 to an. And we can define a transformation T, linear. So just transformation, we'll show that it is a linear transformation. And it is defined by T of x equals to determinant of A1. Let me just use A. So let me use x. Sorry, I should not use x. So let me copy this. So we have, first of all, Tcx equals c times tx. This holds for all c real and for all x n-dimensional real vector. This holds by the above results we just mentioned. And second of all, this equals t of u plus t of v for all uv being n-dimensional random vector, well, just n-dimensional vector. And this linear property of the determinant turns out to have many useful consequences in applications or advanced study in matrix theory. We shall conclude our first lecture by offering some tricks in calculating determinants. So for example, if we are going to compute 1, 5, 0, 2, 4, minus 1, 0, minus 2, 0, we see that, so the first, actually, let's just solve this guy. So if we apply the definition of the determinant, so this is equivalent to solving A11, determinant of A11 minus A12, determinant of A12. So this is plus A13, determinant of A13. Right? Since this is a minus sign, since we have minus 1, 1 plus 2. Okay, so we plug this in. So A11 is 1 times the determinant. So we have already figured out the sign. So we do not need to bother writing the minus 1 to some powers down. We just need to write down the determinant. So we start with 1. We have 4. So we have 4 minus 1 minus 2, 0. And minus A12, that is 5 times 2 minus 1, 0, 0. And the other one is 0 times whatever. And this guy is just 1 times 4 times 0 is 0, and minus 2 times minus 1, which is minus 2. And this guy is just 0, so this is just minus 2. And of course, as we said before, we want to choose a row or column that consisting of as many zeros as possible. So for this guy, a better choice should be this is 3, 2. Okay, so A32, that is minus 2 times minus 1, 3 plus 2, and times the determinant, which is 1, 0, and 2 minus 1. So this guy vanished, and this one is minus 1, and this guy is minus 1. So this guy becomes 1, and times this guy becomes minus 2. So this is easier than a direct application of the definition. We shall introduce another very useful concept called the cofactor. And this could be used as the cofactor expansion. So still given n by n matrix A with entries aij, so we say the ijth cofactor of A is the number Cij given by Cij equals to minus I plus j, determinant of Aij. And we see that the determinant equals to A11 C11 plus A12 C12 plus all the way down to A1n C1n, and this formula is called the cofactor. So let me write this down. So it's cofactor expansion. So that is determinant of A equals to A11 C11 plus A12 C12 plus all the way down to A1n C1n. And we arrive at another result. So the determinant of an n by n matrix A can be computed by a factor expansion across any row or down any column. The expansion across the ith row, for example, is Cij equals to minus 1 I plus j, determinant of Aij. So it is determinant of A equals to AI1 Ci1 plus AI2 Ci2 plus all the way down to AIn Cin. And if we use, so this is for row, if we use column, it is A1j C1j plus A2j C2j plus all the way down to ANJ CNJ. And this theorem is called the Laplace. In fact, we have a more complex version for this guy. But since we are concerning more on the calculation of the matrices, so we do not introduce that one. And if one is interested, one may take the advanced linear algebra, which introduce with different perspective. For example, the instead of admitting that all our random all our variables are from reals, we admit that all our variables are from a field. But anyway, let's go back to our example. So yes, the sixth theorem, the properties of the and the cofactor expansion of the determinant in a way making the calculation easier. However, as we said at the first of this subsection, which is the calculation of the determinants, we offered some tricks in calculating the determinants, which means that there is no effective method in solving all different forms of determinants. So we shall introduce some techniques. The first technique is to choose a row containing as many zeros as possible. We have seen that. So let us do another example. So suppose we're calculating 1, 1, 1, 1, 1, 2, 3, 4, 1, 3, 6, 10, and 1, 4, 10, 20. This is a very complex one, so how do we solve this guy? A direct application of the definition or all the algorithm we have above may be very complex, and one tiny mistake could lead to the whole confusion of the problem. So observe that determinant first. We may see that if we multiply the third row by -1, sorry, and add it to the fourth row, and then we multiply the second row with -1 and add it to the third row. Lastly, we multiply the first row by -1 and add it to the second row. So let's see what we have. So first of all, we start with multiply the third row. So let me use 1, 2, 3, 4 to represent the rows. So -1 times the third row is -1. So let me write this down. -1, -3, -6, and -10. So in the last row, we have 0, 1, and 4, 10. So then we multiply -1 times the second row and add it to the third row. So that is -1, -2, -3, and -4. And we have 0, 1, and 3, and 6, right? And then we multiply the first row by -1 added to the second row. So we have 0, 1, 1, 1. Oh, sorry, it's 0, 1, 2, 3. So the first row remains unchanged, and we see that by doing so, we can do in the cofactor expansion by the first column since it has only 1 on the upper half. So this leads to determinant of A equals to 1 times -1, 1 plus 1, since it's A1, 1, times, times the remaining guy, that is 1, 2, 3, 1, 3, 6, 1, 4, 10. And this guy, since it is just 1, so we can cancel this out. And now we observe this matrix too. we see that the same trick we apply to the 4 by 2 matrix could be applied to this guy too. So we multiply the second row by -1 and add it to the third row, and multiply the first row by -1 and add it to the second row. So this is our, so it's -1, -3, and -6. So the last row becomes 0, 1, and 4. And if we multiply the first row by -1 and add it to the second row, we have 0, 1, and 3 with 1, 2, 3. So still if we choose the first row, first column to do the factor expansion, we have 1 times -1, 1 plus 1 times 1, 3, 1, 4. And this is just 1, and this becomes 4 minus 3, which is 1. So this is one trick for dealing with the determinant of the form. For example, all the column for one column or one row containing the same element. And now we offer another trick. Or actually, we shall introduce an algorithm. That is, we generalize the example 7. So assume we are dealing with x a a a x a a x a and a x. So that is, we have the elements on the column being the same, and the elements on all other are the same too. And since the sum of each column or row is x plus n minus 1 times a. So by adding each column to the first column, or each row to the first row, so we can, by the property of the determinant, we can pluck out the factor x plus n minus 1 times a. So now we will have, for example, if we are dealing with the first row, the first column, we have all the ones, and the remaining and now we can multiply the first row by -1 and add it to all other rows, and this will yield us with a x plus n minus 1 times a. So let me use this guy. Times 1 a, and 0, x minus a, 0, 0, 0, 0, x minus a, 0, 0, 0, 0, x minus a. So now we successfully made everything except on the diagonal being non-zero. And we have, since the first one is 1, so we have x minus a to the n minus 1 times x plus n minus 1 times a. And now we introduce another algorithm. And this is called the Vandermonde determinant. So with the determinant of the form 1, 1, 1, 1, x1, x2, x3 to xn, x1 squared, x2 squared, x3 squared, xn squared, up to x1 to the n minus 1, x2 to the n minus 1, x3 to the n minus 1, and xn to the n minus 1. So the result of this guy is yield by this formula. So for example, we're moving to example 9. If we're dealing with a matrix, for example, 1, 1, 1, let us only calculate a 3 by 3. 1, 1, 1, sorry, and 2, 3, 4, 4, 9, 16. So let us just apply the formula. So that is xi minus xj. That is 3 minus 2 times 4 minus 2 times 4 minus 3. And this equals 1 times 2 times 1. So it is 2. And if we calculate this guy, so we first, so just apply the definition. So we have 1 times minus 1, 1 plus 1. So we expand the first row times 3, 4, 9, 16. And minus 2, 4, 4, 16. And then plus 2, 3, 4, 9. So let us just cancel this and say it is just 1. So we have 48 minus 36 minus 32 plus 16 and plus 18 minus 12. So this is 12, this is minus 20, and this is minus 4, and this is 14, and this is 2. So yes, this formula is very powerful. Okay, so now that summarizes all the materials for the first lecture, which has a topic being the introduction to determinant. And in the next lecture, we shall talk about the matrix. So next lecture is the introduction to matrix. Okay, thank you for watching. See you in the next lecture.